This is brief introduction of my research. As we all know, neurosurgery can be divided into craniotomy, which is open brain surgery, and other is minimally invasive surgery, which is a kind of stereotactic surgery because it makes use of 3D coordinates to locate the target within the confine of brain. Now it is further divided into frame based or frameless. In the frame based, a bulky frame is attached on the head of patient, and though it is very accurate, but it has some serious limitations, like we have to retain the frame as it is from the time of imaging to the time to the day of surgery. So, and second thing is, to affix this frame rigidly, we have to screw screw it to the skull of patient, which is quite uncomfortable to the patient. Whereas in the frameless system, we create a virtual frame using what is something called radio opaque markers. These markers are are pasted on the scalp of patient, and using those markers we can create a virtual frame. Once the virtual frame is established, then surgical tool can be tracked afterwards. So as we can see, the stereo camera based system is most popular system nowadays. It has a wall mounted camera system, and it continuously tracks the surgical tool. Wherever surgeon move the tool, the surgeon can see its visualization and takes the decision. On the other hand, there is something called surgical coordinate measuring mechanism, which is developed in BRC by our group, and this system measured the fiducial marker one by one. And the third one, which is called autonomous neuro-registration based system, it is developed by me in my PhD. So this system, autonomously, I have developed a method so that it autonomously autonomously moves toward the first, second, third, and whatever fiducials are there. It measures its coordinate system, and then we can do mapping to locate the surgical tool. This is algorithm for autonomous neuro registration. As we can see, we have a medical image space which is obtained by stacking the stacking various images in 3D coordinate system obtained from the MRI and CT scan. And other is real patient space, which as name indicate, it's a physical space where real patient and along with surgical robot and other instruments in the operation theater. So neuro-registration is basically a process of establishing relationship between these two coordinate system by measuring certain number of points in both the spaces, and then mapping those points to establish the neuro-registration process. So that afterwards, if we have certain points, say coordinate of tumor, we can transform it with respect to surgical tool. This is a brief video showing how exactly autonomous neuro-registration and neuronavigation works. So first step is measurement of fiducial marker in medical image space. So as you can see in the left hand side, those are the cross-sectional images obtained from the CT and MRI, and on the images are axial, coronal, sagittal, and oblique image as well. So on the right side you can see this 3D model of skull obtained by stacking those two-dimensional images. And so this 3D skull is very useful for measurement of markers. So as you can see, those markers are visible, radio opaque markers are visible in the images, and we are measuring the coordinates of markers in medical image space. So minimum 3 markers are required, but it's better if we have more number of markers visible. to measure those markers. Now second step is autonomous measurement of coordinates in real patient space. So as here you can see the application of my method, the robot autonomously measure the center of fiducial markers in real patient space in the same order in which surgeon measures the fiducial markers in medical image space. So one of the problem is this method eliminates is the problem of correspondence. Like the first marker in medical image is first marker in real patient. So this correspondence problem, it knows, since it takes the information from medical images, it knows the correspondence already. So it autonomously locates the markers in the real patient space, and it fit the contour, and it maps those measure those markers. And finally, after having coordinates in both the spaces, and we obtain the registration matrix, and now it's time to validate to see how exactly it's moving towards the target. As you can see, it has moved. So I have validated autonomous neuro-registration at National Institute of Mental Health and Neurosciences, Bangalore, and ACTRAC, Mumbai. So I validated on various phantoms and vegetable specimen. So what I did, I took the scan of phantom, and I placed the phantom in several different poses, and measured the coordinate using the algorithm which I have developed. And then I tried to relocate the target using the developed method, and I found that overall everywhere in every phantom I found the accuracy is within 1 mm. So now the conclusion is the hands-free autonomous neuro-registration is consistent in high precision. The robot-based neuro-registration eliminates line of sight problem. The robot-based autonomous neuro-registration has resulted in enhanced accuracy in optimal time, and the case studies demonstrated high capability of accessing deep-rooted small-sized tumor with high accuracy.